router solicitation message simply says, I need addressing information from router. So this is the message. In the second phase, we're going to have the device using the local router's ICMP version 6 router advertisement or IRA messages to end up with its prefix length, and other information including DNS and gateway. ICMP version 6 router advertisement or RA messages are sent regularly, let's say every 200 seconds, to all IPv6 enabled devices on the network. And we can have three different options here depending on the configuration that you want for ICMP version 6 router advertisement. With the first option, it's called Slack only. Second option is Slack and DHCP version 6 server. And the third option, or option 3, is DHCP version 6 only. So ICMP version 6 RA messages sent regularly, and devices, they use these sort of messages in order to configure their IP addresses. The whole idea, remember, the whole idea is for a device to obtain its prefix length, default gateway address, and other information from an IPv6 router. The first option is Slack only, stateless address auto configuration. We call it the Slack. With Slack only, the RA message is telling the device that I am everything you need, meaning that I have prefix length, and default gateway for you. And this is RA option 1, Slack only, or the default setting, that is Slack only. With option 2, Slack and DHCP version 6, or in other words, we call it stateless DHCP version 6 address configuration. The RA message includes some information and asks the device to get other information from a DHCP version 6 server. So for this, we can say that the RA include this message. Here is my information, but you need to get other information such as DNS addresses from a DHCP version 6 server. So this is RA option 2, Slack and stateless DHCP version 6. We use Slack for IPv6 global unicast address and the default gateway. And we use a stateless DHCP version 6 server for other information such as DNS address. With the third option, DHCP version 6 only, RA message is simply telling that I cannot help you at all. Ask a DHCP version 6 server for all your information. That is why RA option 3 is known as a stateful DHCP version 6, because we store state and we follow the state for requests. So DHCP version 6 only uses the router link local address for the default gateway and uses the DHCP version 6 server for all other information. In fact, this option 3 is pretty much similar to what we had with DHCP server in IPv4, whereby we gain our IP version 4 address and all information from a server. Here, for having DHCP version 6 server only option, we use this RA option 3 mechanism. What you can see is that when the RA message is option 1 or a Slack, or Slack with stateless DHCP version 6 option 2, so option 1 or option 2, the client must generate its own interface ID. The interface ID can be created using the EUI64 process or can be randomly generated with 64-bit number. Randomly generated interface IDs has application with Windows operating system. So Windows uses a randomly generated interface ID, but here with Cisco we use an EUI64 generated interface ID, and it is represented in binary, and it is made up of 3 parts. Before I go through the 3 parts, remember you have seen EUI64 process once before when I was talking about Cisco IOS routers that generate interface ID for all link local interfaces in a dynamic manner. So Cisco IOS dynamically uses EUI64 process to generate the interface ID for all link local addresses on IPv6 interfaces. However, there was a drawback with that, and that's why we prefer statically configuring the link local addresses in our networking scenarios. But the 3 parts of EUI64 to generate interface ID. First part is a 24-bit OUI from the client MAC address, but remember the 7th bit, that is called the universally or locally UL bit, is reversed. The second part, the inserted 16-bit value FFFE in hexadecimal, and the third part is a 24-bit device identifier from the client MAC address. So 24 plus 16 plus 24 is 64. Next up is subnetting. So far, we have seen different use cases for using broadcasts in Ethernet. We have seen address resolution protocol, which sends layer 2 broadcasts to a known IPv4 address on the local network to discover the associated MAC address. Another use case with broadcasts is different services. For instance, Dynamic Host Configuration Protocol DHCP, which sends broadcasts on the local network in order to locate a DHCP server. We have also seen switches and how switching makes use of broadcasts. Switches, they propagate broadcasts out all interfaces except the one on which it was received. So this is known as split horizon, and it happens with switching, and this is another use case for broadcast in Ethernet. So the takeaway point for you is that you see excessive traffic being generated and produced by different devices and different services and different networking functions. And of course, this degrades the network performance, and it consumes too much bandwidth with unnecessary broadcast traffic, because even those machines not interested or not intended to receive this amount of broadcast traffic will receive it. They have to process it, and it's such a big waste of bandwidth and resources. We would like to reduce the size of the network to create smaller broadcast domains, because with the default setting, all interfaces on a switch are part of the same broadcast domain, and every broadcast will be propagated out all interfaces except the one on which it was received. However, with routers, every single interface is a separate broadcast domain. So routers, they break the broadcast domains into smaller broadcast domains. So these smaller network spaces or sub broadcast domains are called subnets. What are the reasons for subnetting? Well, subnetting reduces overall network traffic and therefore it improves network performance. Also, subnetting enables an administrator to implement security policies such as which subnets are allowed, which subnets are not allowed to communicate together. So, reducing overall traffic and improving performance and also enabling security policies implementation are the main reasons for subnetting. You already know about octet boundary, like subnet mask /8/16 and /24 that we have with classful addresses, and you see how easy it is for the networks to be subnetted at the octet boundaries. Recall that prefix length as well as subnet mask, they are two different terms for the same concept, prefix length or subnet mask. So we identify the network portion and we identify the host portion of an address. A more sophisticated subnetting method, rather than just subnetting at octet boundaries, is to borrow bits from the host portion. So subnets are created by borrowing host bits for network bits. So we borrow from the host portion and add to the network portion. More host bits borrowed, the more subnets that you can define. So the formula 2 to the power of n, whereby n is the number of bits borrowed from the host portion and added to the network portion or network side, is used to calculate the number of subnets. If I borrow 2 bits from the host portion of a/8 network, that simply means that I am having a /10. A new prefix length or the new subnet mask will be /10. And that simply means that I will have 2 to the power of 2 more subnets added to my scenario. So 4 more subnets can be created when borrowing 2 bits from the host portion. For each of these 4 subnets, within each of these 4 subnets, first and last address of each subnet cannot be used as host addresses. I'm talking about the very first and the very last address of each subnet, because the very first one is the network ID and the very last one is the broadcast address for the subnetwork, and therefore they cannot be assigned to host, and therefore they are not host addresses. The formula 2 to the power of n minus 2 is therefore needed to calculate the usable number of addresses or the host addresses, the number of addresses that can be used for host address assignments. In this formula, N is the number of bits for host portion. So let's say we have a slash 30, 30 for the subnet mask. That means we have only 2 bits to be used for the host portion. And that means for each subnet we're going to have 2 to the power of 2 minus 2, which is 2, only 2 usable IP addresses. If you calculate, of course, it gives you 4 different addresses for each subnet, but remember the very first and the very last one are already reserved for the network ID and the broadcast address. That therefore only 2 addresses remain to be used for host assignment. Back to our previous example, whereby you're given a /8 network. /8 means that we are still at an octet boundary, and you want to create 4 different subnets because let's say you have 4 different departments in your business. Then you borrow only 2 bits, so the new prefix length or subnet mask is going to be /10, and you're going to create 2 to the power of 2, that is 4 different subnets with borrowing 2 bits from the host portion and adding that to the network portion. You're going to have a new /10 prefix length. This is traditional subnetting. One mask /10 is used for the whole business, for the entire of your network. Addresses are wasted in traditional subnetting when you use one subnet mask for the whole network, because you rarely have departments in your business with the same requirements, and 4 different departments within a business where each of them they need 2 to the power of 22 different host addresses to be assigned is impossible and is not realistic. That is why instead of traditional subnetting we use VLSM, variable length subnet mask, because VLSM can solve the wasted addresses issues, and you see these issues in particular when you don't have many addresses required. So WAN connections, for instance, for a single WAN connection you only need 2 addresses for each end, and imagine using a /10 prefix length for a WAN connection address assignment is such a big waste. So out of 2 to the power of 22 different host addresses, of course minus 2 because of the very first and the very last one, you only need 2 single addresses for the each end of the WAN connection, and that's it. The rest is just a waste. However, BLSM is subnetting a subnet to create subnets with different number of hosts, unlike the traditional subnetting with one mask for the whole network. So we further subnet a subnet with VLSM. This is very important to remember. With basic VLSM, subnets do not have to be equal sizes. So we don't need to have 4 different subnets all with a /10. We can further subnet those subnets according to our requirements. So subnets, they do not need to have equal sizes as long as their address ranges do not overlap. As a best practice, whenever you're creating subnets, it's easier to work from larger department to the smaller one. So from the largest, let's say, subnet requirement to the smallest one. I have an example here for you with VLSM. Imagine that you are given the network 172.16.0.0/23, and the requirements for your network is that you need one subnet with 200 hosts, you need one network with 100 hosts, one network for 50 hosts, one network for 25 hosts, and one network for 10 hosts. You also have, let's say, 4 point-to-point networks, so 4 WAN connection, for instance, and with each you need 2 hosts to be addressed. So 4 times 4, you need 16 subnets, each of which with 2 address requirements for connections. As you can imagine, a /23 prefix length or subnet mask simply means that your host portion is going to have 9 bits. And that simply means that you can provide addresses for 2 to the power of 9 hosts. That is going to be 512. Is that enough? Yes, it is, because if you add your current network requirements, which is 200 plus 100 plus 50 plus 25 plus 10 plus 16, then of course you have more than enough. You also cater for the growth of this network, so the future expansion to a limit with /23. As I said, we always start with the largest department. So your largest department has 200 hosts. That simply means that with 8 bits to be borrowed from the host portion, I can have 2 to the power of 8, 256 minus 2, of course, for the very first and for the very last address. So 254 usable addresses for hosts can be achieved. And that simply means that I can not only cover 200 hosts that I'm having at the moment for this big, large department, but also I can have 54 more addresses to be used for future growth of this department if, let's say, new employees are coming. So my new subnet mask is going to be /24 instead of /23 because I'm borrowing one more bit from the host portion and add that to the network portion. My initial network portion had 23 bits prefix length, and now with borrowing one more bit from the host portion and adding that to the network portion, my new prefix length or my new subnet mask is going to be a /24. And that simply means that I'm going to have 172.16.0.0/24, my first subnet with 256 address, and 172.16.1.0, again a /24 with another 256 addresses to be used. Of course, the first one, 172.16.0.0/24, is the one that I am going to use for my first department in the business. And I can provide addresses immediately to 200 machines and also have 54 addresses to be used for the near future. The second address, 172.16.1.0/24, I don't need it because it's too big and my requirements are less than that. So let's break it down, and that is further subnetting a subnet, or that is VLSM. My second requirement on my list is one network for 100 hosts, or my second department, let's say. That simply means that if I am having 7 bits for the host portion, then that means I'm going to have 2 to the power of 7 minus 2 usable addresses. So 128 minus 2, 126. Whereas my actual requirement is only 100 hosts. So I can not only cover that, but I can also have 26 more addresses to be used if the business or if this department, let's say, grows over the time. That simply means I'm going to have a new prefix length /25, and the first 2 subnets within that range is 172.16.1.0/25 and 172.16.1.128/25. The first will be used for the department with 100 hosts requirement. The second one, we don't need to waste it. It's a big subnet. Let's break it down. Let's further subnet this subnet for the third requirement on my paper, which is a network or the third department with 50 hosts. As you can see, we continue this process up until we provide IP addresses for connections, let's say for WAN connections, whereby we only need 2 IPs for each end of a single WAN connection. And that is going to be /30, whereby we have only 2 bits in the host portion, and that's going to give me 2 to the power of 2 minus 2, or 4 minus 2, which is 2 usable addresses for each of these subnets. After we have identified our addressing scheme, of course we can use DHCP so that end user clients can be set for DHCP to save time and manual errors. So we automatically assign IP addresses. However, a change in the subnetting scheme requires reconfiguration of DHCP server. This is important to remember. For IPv6, clients can also use DHCP version 6, and also they can use Slack that we have seen previously. Which devices require addresses? End users, end user clients machines that we have seen. Servers, of course, they need addresses. However, unlike end users with servers, we want to know addresses, exactly which address is assigned to which server, because we want to use that address for different purposes in the network, and therefore we don't want it to be changed each time that DHCP is running. Therefore we use static addresses. We don't assign addresses to servers using DHCP typically. So servers are configured with static addresses. And another lesson to remember is the fact that we use network address translation if we are using any private addresses inside our network. So if the server address is from the private address range, then that needs to be translated to public addresses so that they can be accessible from the internet. So servers can be accessible from the internet. So NAT sits in the middle of communication. That is to do with IPv4, not IPv6. The third category of the devices that need IPs or addresses is intermediary devices, routers, switches, networking devices that are known as intermediary devices. They need also to be set with static addresses. So one application for static addresses is servers, another application is intermediary devices. Why does a switch need uh, an IP address? Because we want to get to that switch remotely if we want to do some remote management, and therefore that switch needs to be identified at the network layer as well. So intermediary devices, they're set with static addresses for remote management. Fourthly and finally, gateway, the taxi towards our remote networks, or a taxi out our local network. Router interface that is used as a gateway needs to be addressed in order to exit the network. Next, about IPv6 global unicast address. We want to know if we have subnetting, the same concept for IPv6. Yes, we have, and if we want to use subnetting for IPv6, then we are using what we know as subnet ID. It is important to remember that the structure for IPv6 address is that we have typically a 48-bit global routing prefix. Then we have a 16-bit subnet ID that is used for subnetting. And the third part, that is the interface ID, is 64-bit. You know about EUI process if you want to randomly generate interface ID. Now we want you to know that the subnet ID section with 16-bit length can also be used for subnetting purpose. IPv6 subnetting is not concerned with conserving address space because we have enough number of addresses that we think at the moment. IPv6 subnetting, however, is about building an addressing hierarchy based on the number of subnetworks needed. We don't have IPv6 link local addresses to be subnetted, so link local addresses are never subnetted. IPv6 global unicast addresses, however, can be subnetted. IPv6 global unicast address, as I said before, normally consists of a 48 global routing prefix, a 16-bit subnet ID, and a 64-bit interface ID. Three main components that together made up IPv6 global unicast address. The 16-bit subnet ID is used for subnetting. What about global routing prefix? Well, this is the prefix or network portion in IPv6 of the address that is assigned by the provider. So global routing prefix is typically assigned by the provider regional internet registries, what we know as RIRs, RIR entities, regional internet registries. RIRs assign a /48 global routing prefix to ISPs and other customers. So that is determined by RIRs entities. Subnet ID is used for subnetting, and interface ID, by now you know that it is configured using EUI 64 process if we want to create it randomly. Next stop is transport layer. Transport layer mediates between application layer and the lower layers of the reference model that are responsible for network transmission. Transport layer establishes a temporary communication session between two applications, one on the source side and one on the destination side, and ensures the delivery of data between source application and destination application. Responsibilities of transport layer include tracking the conversation, segmentation of data, and identifying the application. By tracking the conversation, what we mean is to track each individual conversation flowing between a source application and a destination application. Segmentation is about dividing the data into segments that are easier to manage and to transport. For this purpose, for segmentation and also for identifying the application, we need header layer for header or transport layer header that is used for reassembly at the destination side and also is used for tracking conversation and tracking different segments. Identifying the application is the third responsibility of transport layer. We ensure that even with multiple applications running on a device, all applications receive the correct data via port numbers. So in order to identify applications, we use port numbers. I would like you also to know about multiplexing, and conversation multiplexing is a very important concept. When we segment data into smaller chunks, in fact, we enable many different communications to be multiplexed on the same network. When we say to be multiplexed, what we mean is to be interleaved. You know that to interleave means to insert pages. Let's say typically blank ones, blank pages are interleaved between the pages of a book, and here we do the same. Smaller chunks of data, they are multiplexed on the same network, and segmenting data into smaller chunks to be multiplexed is what happens thanks to transport layer. TCP/IP reference model provides two transport layer protocols: Transmission Control Protocol or TCP and User Datagram Protocol or UDP. TCP is considered reliable, which means that it ensures all of the data arrives at the destination. It also ensures that with the additional fields in place inside the header, we don't need to manage reliability ourselves, but instead TCP ensures reliability. So TCP is considered reliable because it ensures that all of the data arrives at the destination. For this purpose, we need additional fields in the header of transport layer. These additional fields, it means that we're going to increase the size and of course the delay. However, TCP frees application from having to manage reliability by themselves. Different applications, you know about HTTP, they use TCP, HTTPS, FTP, SSH, SMTP, Telnet, they all use TCP for transport layer. HTTP port number 80, HTTPS port number 443, FTP uses both port number 20 for data and port number 21 for control. SSH uses port number 22, SMTP uses port number 25, and Telnet that uses port number 23. They are all based on TCP for transport layer. User Datagram Protocol UDP does not provide for reliability, and that means we're going to have fewer fields, and that in turn means that we're going to have faster transport layer protocol than TCP. Three types of applications that best suited for UDP: applications that are based on live video and multimedia. Secondly, applications that are simple request and reply in nature. And thirdly, applications that can handle reliability by themselves. So some examples in today's networks include DHCP. DHCP uses UDP port number 67 for the server side and 68 for the client side. DNS, of course, DNS uses both 53 for UDP and TCP 53 as well. SNMP uses port number 161, and trivial FTP or TFTP uses port number 69. Other applications like VoIP or IPTV, so they both use UDP for transport layer. We can use sending mails and different types of postages possible for clarification for comparison between UDP and TCP. UDP is similar to a non-registered letter when you send it. This means that UDP is a stateless protocol and reliability is not the main concern. It is assumed that reliability with UDP is handled by higher layers, application layer. TCP transport, however, is similar to sending tracked packages. If a shipping order is broken up into several packages, that means a customer can check online to see the order after delivery. And this is exactly what happens with TCP. That's why TCP has applications in databases, in web browsers, and email clients. They all require that the data that is sent arrives at the destination in its original condition. UDP, on the other hand, doesn't care if one or two segments of a live video stream fail to arrive. If disruption in the stream may not be noticeable to the user, then we can try UDP instead of TCP. IP telephony or VoIP and streaming video are two famous applications of UDP. So, in order to ensure reliability, TCP has three responsibilities to take care of: numbering and tracking data segments, acknowledging received data, and thirdly, retransmitting any unacknowledged data after a certain period of time. In detail, there is a timer, and when the time expires, we ask for retransmission of any unacknowledged data. TCP features: we establish a session, and that's why we call TCP a connection-oriented protocol, because a temporary communication session is needed to be established between source and destination before the actual transport happening. Another feature of TCP is that we ensure that the application on the destination side is ready to receive the data before we send it. We need to negotiate the amount of traffic that can be sent and can be forwarded at a given time with the destination side. Another feature for TCP is reliable delivery, ensuring that each segment that the source has sent arrives at the destination. Same order delivery, very important, and for this feature we use numbering and sequencing the segments in order to guarantee reassembly into the proper order at the destination side. TCP provides flow control mechanism so that we can regulate the amount of data that source transmits. As a result, you can see establishing session, reliable delivery, same order delivery, and also flow control are four different features or significant features of TCP. UDP, on the other hand, is known to be an unreliable transport layer protocol. So we describe it as best effort transport layer protocol. There is no acknowledgement required, and it's known as a stateless protocol. Of course, this is not bad because we have smaller header size, and that means we're going to have less overhead. So UDP is a preferred transport layer protocol for live streaming, for video, and also for voice applications, whereby a few segments drop or failure do not make any changes or any noticeable changes to the end user experience of the application. The figure here on the top is TCP header, 20 bytes TCP header, and towards the bottom of the slide you can see the UDP header, and you can notice the difference in size. UDP header is much smaller. TCP header fills what we have inside this 20 bytes. Header includes source and destination port. They are used to identify application. We have seen some examples before. We also have a field for sequence number, and that field is used for data reassembly later at the destination site. With the same size, we have acknowledgement number field, indicates data has been received and ready for next byte from source to be sent. Header length, that specifies length of TCP segment header. We have control bits, that explains the purpose and function of that specific TCP segment. And then we've got window size to be used with flow control to regulate the amount of data that source transmits. Number of bytes that can be accepted at one time is referred to as window size. Then we have checksum, and checksum within TCP header is used for error checking, not only for segment header but also for its data, so it covers both. Imagine that users expect to simultaneously receive and send email via electronic mail POP3 protocol. They want to simultaneously view websites thanks to HTML and make a VoIP phone call with internet chat protocol or IM protocol. They want to use instant messaging capability. So how to distinguish different applications? TCP and UDP, they manage multiple conversations by using unique identifiers, and these unique identifiers are called port numbers. Electronic mail POP3 protocol, port number is 110. HTML page is requested on port 80, or IM protocol uses port number 531. So unique identifiers or port numbers are used for TCP as well as UDP in order to manage multiple conversations. We have source port and we have destination port. Source port indicates the originating application port that is dynamically generated by sending device. An example of that is each separate HTTP conversation, for instance, is tracked based on the source ports. Destination port, on the other hand, tells the destination what service is being requested. For example, when you're using web browser to get to www.yahoo.com, then you are requesting a web service running on port 80 at the destination site. So port 80 web services are being requested. So once again, source port specifies the originating application port that is dynamically generated by a sending device, and destination port tells the destination what service is being requested. What happens at the end of the day is that source and destination ports are placed in a header inside the segment, and then segments are encapsulated in IP packet, and what you can see is a combination of IP plus port number. This combination, IP plus port number, is called a socket. Example, if the IP address is 192.168.1.7 for the destination web server, Then the port number 80 for web services request on that site, and that means that the socket 192.168.1.7:80 or 80 forms the socket here. Sockets enable multiple processes to be distinguished. So we use a combination of IP in addition to port number so that we can differentiate multiple processes from each other. Source port here acts as a return address. So we are telling the web server in this example how to get back to us, or we provide the return address with the source port when we contact the web server. This is also important for you to know different ranges defined for port number groups. We have well-known ports, we have registered ports, and we have dynamic or private ports. Well-known ports, numbers between 0 to 1023 or 1023, these numbers are reserved for services and applications. So well-known ports like HTTP or HTTPS. Registered ports ranges from 1024 to 49,151, 49151. These port numbers are assigned by IANA to a requesting entity to be used for specific processes or applications. Dynamic or private ports ranges from 49,152, 49,152 to 65,535 or 65535. This range usually assigned dynamically by the client's operating system and used to identify the client application during communication. This dynamic or private range is what we earlier described for source port when we say that it indicates the originating application port that is dynamically generated by sending device. And this is the way that, let's say, we can differentiate different HTTP conversations being generated from us to specific web servers. The way that we can track them is by using dynamic or private ports being generated dynamically and being used as the return addresses. Next stop is application layer. Application layer, based on the OSI reference model, is the 7th layer, and then the 6th layer is presentation, and the 5th layer is the session layer. Application layer is the closest layer to the end user, to us, to humans, and is used to exchange data between hosts, and in this case between source host and the destination host. So programs running on hosts, and application layer is responsible for exchanging data between these programs running on the source and destination hosts. Application layer, you know different protocols from this layer. Very famous one, DNS, domain name system. HTTP is a protocol running on application layer. So it's hypertext transfer protocol, HTTP. We have simple mail transfer protocol. So hypertext transfer protocol, simple mail transfer protocol, SMTP. We have POP3 or post office protocol for emails. We have dynamic host configuration protocol, DHCP, very famous one, used to give IPs to the machines as soon as they come up. We have FTP to share files. We have file transfer protocol, FTP. Another famous protocol for emails, IMAP or Internet Message Access Protocol. So they are all different examples for application layer serving different purposes. Then we have 6th layer, that is presentation layer. Again, you know very famous standards. So standards and functions like QuickTime, MPEG, Motion Picture Express Group. We have GIF for images. This format is very famous graphic interchange format GIF. We have JPEG format, Joint Photographic Express Group, and in today's internet, very famous one, PNG, Portable Network Graphics. These are different presentation layer functions and standards. Presentation layer in particular has three different tasks. Let's see what three different responsibilities of presentation layer are. We have formatting for formatting data at the source device into a compatible form for the receiving device. So source device must care about what receiving device can in fact receive. That's why source device needs to format data into a compatible form for the receiving side. Second task with presentation layer is to compress data, and the third task, of course, is encrypting data so that if the message is received by an entity in the middle of conversation, it is not readable. This is presentation layer task. Then we have session layer, or the fifth layer of OSI model, that is used to create and maintain dialogues between source and destination applications. Back to TCP/IP reference model, we are talking about application layer as the fourth layer, and we're going to have different applications and we're going to go through them in more details. We have domain name server DNS, and DNS is a application layer protocol that is running on both TCP as well as UDP, and it uses port number 53 for each. DNS is there to translate domain names into IP addresses, because we humans are good with names, but we are not good to memorize numbers. That's why we know what cisco.com is, but we don't know the IP address, the specific IP address assigned to the cisco.com, for instance, here. So we need DNS to translate domain names such as cisco.com into IP address for us, because networks and computers, they are working in binary and in numbers. Then we have bootstrap protocol, bootp. Bootp, we don't go through the details because it is superseded by DHCP, Dynamic Host Configuration Protocol, a protocol that is working over UDP in transport layer. In more details, it uses client port number 68 and server port number 67. So 67 for server, 68 for client, and UDP is the transport protocol. DHCP is there to dynamically assign IP addresses to machines and to client stations as soon as they come up. So at startup, if they don't have static addresses configured on them. Then we have three protocols to be used for emails: SMTP, or Simple Mail Transport Protocol. We have POP3, or Post Office Protocol, and then we have IMAP, Internet Message Access Protocol. SMTP operates over TCP port number 25, POP3 operates over TCP 110, and IMAP operates over TCP 143. So the takeaway point for us is that all email protocols here, these three, are running over TCP. in other words, reliable and connection-oriented, are required for emails to operate. We have SMTP that enables clients to send email to a mail server. Then we have POP protocol to enable clients to retrieve emails from a mail server. And when we retrieve emails from a mail server, there is no copy left on the server side. However, we have IMAP to enable clients to retrieve emails from a mail server, but also to maintain a copy or copies of emails on server. Then we have FTP, file transfer protocol, and trivial file transfer protocol, TFTP. FTP uses TCP, unlike TFTP that operates over UDP. FTP uses TCP port number 20 and TCP port number 21, whereas TFTP uses UDP port number 69. FTP, by using TCP, can be seen as a reliable, connection-oriented protocol that provides acknowledged file delivery. TFTP, trivial one, on the other hand, is a simple protocol and it's just a connectionless file transfer protocol. Then we have Hypertext Transfer Protocol, HTTP, and also we have Hypertext Transfer Protocol Secure, HTTPS. HTTP operates over TCP port 80 or 8080. HTTP, in fact, is a set of rules for exchanging texts, graphic images, etc. on the www World Wide Web. HTTPS is the secure version of HTTP that uses encryption and authentication to secure communication, and it operates over TCP and UDP port number 443. Although HTTPS can run over TCP as well as UDP, it is not expected to run over UDP, which is an unreliable datagram protocol. Next, I would like you to know about two models for networking. We have client-server model and we have peer-to-peer model. With client-server model, we are having client processes and we are having server processes. Client and server processes are considered to be in the application layer. That means that application layer protocols, or seventh layer of OSI model, they describe the format of the requests from clients to servers and responses from servers to clients. So the format of the requests and responses between clients and servers are determined by application layer protocols running client-server model. Example of a client-server network is emails. When you are using your local ISP's email service to send or to receive and store emails. In fact, behind the curtain, you're using a client-server architecture for networking. Another example for client-server model is Hypertext Transfer Protocol, HTTP, when a web address or a URL, Uniform Resource Locator, is typed into a web browser. The web browser establishes a connection to the web service running on the server using the application layer HTTP protocol. So we are learning here that HTTP is a request and response protocol, or a client and server protocol, that in response to the request from a client HTTP server returns what we know as HTML code for a web page, and then your browser interprets the HTML code. Remember, HTML is a markup language, and your browser here acts as an interpreter in order to display a web page based on markup code or HTML code. On the other hand, the application layer defines the format for the protocol message or messages exchanged between the client and the server. In this case, with HTTP, we're going to have three famous message types, three common message types of HTTP. We have GET, we have POST, we have PUT. So with GET, a client request for data is dispatched from a client to server. With POST, a client can upload data files to the web server, and with PUT, a client can upload resources or content to the web server. So POST for data, PUT for content. HTTPS, again, a version of HTTP that supports security and is the baseline these days for World Wide Web. The protocol uses encryption and authentication to secure data. So this is the first model, client-server model, and the topic for our discussion here is how application protocols interact with end-user applications. The first architecture, client-server. The second architecture is peer-to-peer. With peer-to-peer, data is accessed from a peer device without the use of a dedicated server. In other words, with peer-to-peer, all devices are considered equal in communication process. Each device, known as a peer, can function as both a server as well as a client. We have a peer-to-peer application in this architecture to allow a device to act as both a client and a server within the same communication. Peer-to-peer applications require that each end device provide a user interface and run a background service. Common peer-to-peer networks include G2, Bitcoin, BitTorrent, and ITN. Some of them you may have heard about it. Some peer-to-peer applications are based on GNutella protocol, where each user shares whole files with other users. Some other peer-to-peer applications, they allow users to share pieces of many files with each other at the same time. Very famous BitTorrent technology operates in this way. So GNutella protocol shares whole files, whereas other peer-to-peer application may just let you share pieces of many files with each other. The takeaway point for us here is that in peer-to-peer model, A device acts as both client and server within the same communication, and that means that devices are considered equal in communication process. Now we are going to see more details of some client and server model applications. Let's start with email protocols, whereby email clients they communicate with mail servers in order to send and receive emails. Mail servers in turn can communicate with other mail servers in other domains in order to transport messages from one domain to another. So you start with client to server, meaning that your email client software running on your machine communicates with mail server of your local ISP, and then you may have a chain of servers communicating with each other, and in order to travel between different domains to get to the appropriate domain at the end and retrieve the email from there. We have seen SMTP to send emails, we have seen POP to retrieve email, and we have said that POP is used to retrieve email from a mail server in a way that email is downloaded from the server to the client, and that means that that copy is no more on the server, so the email is deleted on the server and will be downloaded locally from the server. Then we have IMAP. IMAP, unlike POP, let the copies of a message be downloaded from the server to the client, but the original messages are stored on the server. So similar to POP, IMAP is used to retrieve mail from a mail server, but copies of messages are downloaded from the server to the client, and the original messages are stored on the server. Another example of client-server model is DNS to resolve names to addresses. Domain name service, as the name suggests, domain names convert the numeric addresses into a simple recognizable name. Because as I said, we are good with names, with memorizing names, but we are not good with memorizing numbers equally. DNS protocol defines an automated service that matches resource names with the required numeric network addresses. When a client makes a query, the server's DNS process first looks at its own records to resolve the name. What if he couldn't find any relevant record? If unable to resolve, then it contacts other servers to resolve the name. The server temporarily stores the numbered address in the event that the same name is requested again. So in other words, it uses caches. It caches the numbered address. Your Windows-based PC, if you issue ipconfig/display DNS, this command displays all the cached DNS entries on a Windows PC. Another important point about DNS to remember is that DNS is a hierarchy of DNS servers, in fact, that contains resource records, or RRs, that match names with addresses. The hierarchy is as follows. On your machine, you have DNS client, and DNS client's contacts local DNS server of your ISP. Local DNS server of the ISP is called secondary level domain servers. Local DNS server or secondary level domain servers then contact top level domain servers. And top level domain servers, they contact root DNS servers if needs be. So local or secondary level domain servers, one layer of hierarchy, the second layer of hierarchy, top level domain servers, and the third layer of the hierarchy is root DNS servers. DNS message format, we have header, we have question. Question is for the name server, you're asking question. Then the answer points to the resource record that answers your question. So RR answering question. Then you have authority field, resource record that points to an authority. And then finally you have additional field in case resource record is holding additional information. So these 5 header, question, answer, authority, and additional are inside DNS message. Included fields within DNS message. Next, client server based application. We want to see is Dynamic Host Configuration Protocol DHCP. For IPv4, this protocol automates the assignment of IPv4 addresses. Not only addresses, but also assignment of subnet masks, gateway addresses, and other parameters are done all thanks to DHCP. DHCP distributed addresses are leased for a set period of time. That means next time you reboot, you may get another address, not the same one. Then the leased addresses are returned to the pool for reuse. DHCP is usually employed for end user devices. So what about devices like gateways, networking devices like switches or servers or printers? For network devices, we usually use static addresses instead of dynamic addresses. So we don't need DHCP for networking devices. How about IP version 6? DHCP version 6 is here to serve the same functionality of DHCP for IP version 6, provides similar services for IPv6 clients. DHCP uses 4 different messages, and you can see in this slide towards the bottom the figure displays 4 different messages and their use cases: discover, offer, request, and acknowledgement for ACK. So the first message that DHCP is using is sent from client to broadcast address. DHCP discover. The device announces that he needs IP address using a broadcast communication type. Then server, or the closest server to him, responds with DHCP offer unicast message type. Then the client or the machine that needs address reacts with another broadcast message, DHCP request. And then the server again comes back to the client with DHCP acknowledge. So this means that what you can see in red in this figure is broadcast message, DHCP discover message. DHCP client sends a DHCP discover broadcast on the network in order to find a DHCP server. If there is no response from a DHCP server, what would happen? That means the client assigns itself an APIPA, automatic private IPv4 address. We have seen APIPA before. DHCP offer message comes from the server on the network, and the server that receives a DHCP discover message now responds with a DHCP offer, which offers the client an IPv4 address lease. DHCP request, thirdly, client accepts the first offer received by broadcasting a DHCP request message for the offered IPv4 address. And DHCP acknowledgement, fourthly, the server accepts the request by sending the client a DHCP acknowledgement message. So this is also important to remember that DHCP is not limited to these 4 messages only. There are more messages, but these are the most important ones to remember. Then we have FTP, File Transfer Protocol, as another famous client-server based application. FTP requires 2 connections, remember, between the client and server. One connection is needed for commands and replies, and another connection is needed for the actual file transfer for data. So between the client and server, 2 connections are established. One for commands and replies, the other for the actual file transfer. The client establishes the first connection to the server for control traffic. That means commands and replies using TCP port number 21. The client also establishes the second connection to the server for the actual data transfer using TCP port number 20. That's why with FTP you are using 2 different TCP ports. One for control traffic for commands and replies, and another for actual data transfer. Last but not least, SMB, or Server Message Block, a Microsoft networking solution. Important to remember, it is used for file sharing and print services, and it has become the mainstay of Microsoft networking. Clients using SMB establish a long-term connection to servers. So another famous example of client-server based model applications is SMB. Clients establish a long-term connection to server and can access the resources on the server, as if those resources are local to the client host. So Microsoft networking for file sharing and a client server or a request response based protocol, SMB. Next up is putting all the previous elements together in order to build a small network, and then see how network security fundamentals look like for such a small network. First, which factors to consider when designing and implementing a small network is important. Remember, in today's world, the majority of businesses are small and typically require small networks consisting of a single router with 1 or more switches, and possibly you're going to have 1 or more wireless access points. The business might also have IP phones, and for the internet connection, that single router will normally have a single wide area network connection, WAN connection, using DSL, using cable, or using an Ethernet connection to ISP. Here I'm going to talk about 6 basic elements of designing a small network. So 6 basic factors to consider when designing and implementing a network, in particular a small one, and later you will see even with large ones they follow the same structure. Device selection criteria, or the first factor, planning IP addressing, is the second factor to consider when building a small network. Reliability and how you want to provide reliability is important. Traffic management is very, very important. Scalability, and finally, network security. These 6 elements together need to be thought of in advance before building a small network. Although I'm emphasizing on a small network here, you need to remember that even for large networks, we follow the same criteria. Regardless of the size of the network, all networks require planning and design in order to ensure that all requirements, cost factors, and deployment options are considered before actual implementation of the network. Device selection itself includes certain criteria. We need to consider cost, we need to consider ports, speed, expandability, and manageability. With cost, what we mean is the cost of hardware, here switches and routers. So the cost of a switch or router is determined by its capacity and features. Ports need to be considered in advance. We want to see exactly what speed we need and the types of ports and interfaces for networking devices. Choosing the number and types of ports on a router or switch is an important decision to make. Expandability. Networking devices, they come in both fixed as well as modular physical configurations. And with modular configurations, it opens up the door for expandability and flexibility of the network. Next, manageability of the network is important. For this, operating system features and also services need to be studied. We need to know exactly features and services that we're going to have in our network, including security, quality of service, voice over IP, VoIP, if we have any layer 3 switching, or if we have NAT, network address translation, and DHCP in place. These services and operating system features all need to be considered for manageability of our small network later. Next criterion to consider before implementation is the IP addressing plan, or planning the IP addressing for your network. It helps us track device types, different types of devices will factor into the IP design, including end devices for users, servers and peripherals, hosts that are accessible from the internet, intermediary devices. For all of them, IP addressing space must be planned when implementing a small network. All hosts within an internetwork must have a unique address so that we can distinguish one machine from another. Planning and documenting the IP address scheme, not only planning but well documenting it, helps administrators track device types, as I said. It also provides easier traffic identification. For example, if all servers are assigned a host address in the range of, let's say, 50 to 100, then it is very easy to determine server traffic by their IP addresses. So easier to identify traffic as well. Next design criterion to think about is reliability of the network and how we use redundancy in order to provide reliability for our network. Reliability is a very important element of network design. This is because a network failure can be costly, and we want to avoid any cost incurred by failures to our network and consequently to our business. A data center network, for instance, can have four types of redundancy in order to provide reliability. In this example, we can have redundant servers, redundant links, redundant switches, and redundant routers. You can see redundancy in four different layers. So a server, a link, a switch, or a router, they all can fail, and the network would still continue to function. And this is what we're aiming at by reliability and redundancy here. Next network design criterion to consider is traffic management and the way that we prioritize traffic. The types of traffic and how traffic should be handled should be considered wisely in advance, and in particular, sometimes we need to prioritize some type of traffic in the network design. Routers and switches are devices that in a small network should be configured in order to support real-time traffic. And when I say real-time traffic, I mean voice and video traffic, for instance. So these two types of traffic need to be prioritized in the network design. In a normal scenario, when we have voice, video, let's say some SMTP traffic, some IM or instant messaging traffic, and some FTP traffic, then probably voice and video, they need to be prioritized as urgent traffic. So high priority will be assigned to voice and also to video traffic. SMTP medium priority, IM or instant messaging normal priority, and FTP has the lowest priority in this example. Network traffic should be classified according to these priorities in order to enhance productivity of employees and in order to minimize network downtimes. To know about traffic management in details, we need to know common applications that we have. There are two forms of software programs or processes that provide access to the network. These two forms of processes include network applications and secondly application layer services or layer 7 services. When we say network application, we mean the software programs used to communicate over the network. Some end user applications are network aware, and by network aware we mean that they are able to communicate directly with the lower layers of the protocol stack. Examples of network applications include email clients and web browsers. So your Firefox browser, for instance, is a network application. Second form of software programs or processes is application layer or layer 7 services. These are other programs that need the assistance of application layer services in order to use network resources. Examples include file transfer or network print spooling. So to revise, network applications like email clients or web browsers, they communicate directly with the lower layers of the protocol stack, whereas application layer services or layer 7 services, they need the assistance of application layer services, as the name suggests, in order to use network resources. An example of that was file transfer. Next, you need to know about protocols. Each application or network service uses protocols. Protocols define the standards and data formats to be used to format and direct data. Most network professionals work with network protocols, and that's why your job is to know about network protocols in details, because these network protocols, they support the applications. In other words, they support network applications and services. So they support email clients, web browsers, file transfer, network print, spooling, all the examples that we had with network applications and application layer services used by employees in a network. They all rely on protocols, and that's why your job is to know about these protocols. Each of these network protocols, they define processes on either end of a communication session. In addition, they define types of messages to be distributed between source and destination protocols. Protocols also define syntax of the messages, a set of rules to determine if a certain string of words form a valid sentence. This is what we mean by syntax, and in the context of network protocols, the syntax of messages are defined by protocols. And then we're going to have some fields inside messages of that specific protocol, and the protocol is supposed to define the meaning of information within these fields. Protocol defines how messages are sent and the expected response. Finally, protocols define interaction with the next lower layer. Next, design consideration, the fifth one, is scalability. The network administrator must allow for growth for small businesses and their networks. In an ideal situation, the network administrator has had enough lead time to allow the network to grow in line with the growth of the company. In order to scale a network, we need 4 considerations. So the following are required. We need documentation, we need inventory, we need budget, and we need traffic analysis information. With network documentation, not only physical but also logical topology information are required. We then need device inventory, list of devices that use or comprise the network. Thirdly, we need budget. We need itemized IT budget, including fiscal year equipment purchasing budget. Finally, and also interestingly, we need traffic analysis for scalability of our network. We need to know about protocols, applications, and services, along with their traffic requirements. All these info, they need to be well documented, and we need that in advance before thinking about scalability and for our network to grow in line with the growth of the company. Next stop is network security. We know that computer networks are essential to everyday activities. We are aware that individuals and organizations very much depend on their computer networks. We want to see who hackers are, because an intrusion by an unauthorized person can result in costly network outages and loss of work. Attacks on a network can be devastating and can result in a loss of time and also money. Intruders can gain access to network through software vulnerabilities firstly, hardware attacks secondly, or simply by what we know as password guessing. So, hardware or software vulnerabilities. These intruders are called hackers. We have four types of threats in our network. We should be aware of that. Threats can be in the form of information theft, data loss and manipulation, identity theft, and disruption of service. Information theft is about stealing confidential information. So, information theft happens when someone breaks into a computer for the purpose of stealing confidential information. Second types of threats, data loss and manipulation. This is breaking into a computer to destroy or to alter data records. So we have some data records, and the aim of the attacker is to break into a computer in order to destroy or alter that information. An example of data loss can be a virus that reformats a person's hard drive. Manipulation example, we can have an attacker breaking into a system in order to change the price of an item. Let's say we have an online shopping website. Third type of threats is identity theft. This is a form of information theft where personal information is stolen in order to steal someone else's identity. Fourth type of threats is disruption of service. This is preventing legitimate users from accessing services to which they should be entitled. Next up is physical security. And physical security is of paramount importance. What we mean by hardware threats is, in fact, the physical damage to equipment, including servers, routers, switches, cable implants, and workstations. Second class of physical security has to do with environmental threats, temperature extremes, or humidity extremes. So if we have too hot or too cold environment, they pose risks. Third class of physical security threats include electrical threats. What we mean by electrical threats is voltage spikes. If we have insufficient supply voltage, also known as brownouts, if we have unconditioned power, or if we have power outages. What we mean by power conditioning is, in fact, modifying the power in order to improve its quality. We use UPS, uninterruptible power supply, in order to switch off of mains power in case a transient or a temporary condition on the line exists. Fourth class of physical security and the threats associated include maintenance threats. As a result of poor handling of electrical components, we may have electrostatic discharge, or in situations we don't have critical spare parts. Lack of critical spare parts is another maintenance threat example. Or poor labeling. If we have, let's say, our cabling closet With poor labeling, we are posing maintenance threats. Next, we would like to see types of vulnerabilities possible in our network. First, let's define what vulnerability means. Vulnerability is the degree of weakness which is inherent in every network device, including routers, switches, desktops, servers, security devices. But typically, servers and desktop computers are the devices under the attack because this is where we store our information, our asset, our valuable things. Here we're going to talk about three primary vulnerabilities, and remember that these vulnerabilities, these three classes, can lead to different attacks. We can have technological vulnerabilities, we can have configuration vulnerabilities, we can have security policy vulnerabilities. With technological vulnerabilities, weakness within insecure protocols, operating system, and network equipment weaknesses can be exploited. Pay attention to the words that I'm choosing. Vulnerability, assets, to be exploited, lead to attacks. When I say vulnerabilities lead to attacks, these are in fact technical language that we use within cybersecurity and in particular network security. We see more examples later. With configuration vulnerabilities, what we mean is in fact unsecured user accounts. When you use default username and password, let's say, or system accounts with easily guessable passwords, misconfigured network equipment, they are all categorized under configuration vulnerabilities. The third class of vulnerabilities includes security policy. In fact, lack of a written security policy is what we mean here. It may seem boring, but it is absolutely necessary to have a written security policy for your business. Inadequate monitoring and auditing of the network and resources is another type of security policy vulnerabilities. Now we move on to network attacks. Network attacks can be categorized under three primary groups. We can have reconnaissance attacks, access attacks, and DOS attacks. But add to that the malicious code or malware and the opportunities that it provides to attacker to later conduct any of those three primary attacks. That's why together I discussed them in four different groups: malware, reconnaissance, access, and DOS. Variants for network attacks. We're going to have malicious code being discussed first, and in addition to that, networks can also fall prey to various network attacks. Three major categories include reconnaissance, access, and DOS. Malware or malcode is short for malicious software. Software or code that is designed to damage, to disrupt, to steal, or to inflict damage on data, on hosts, and on networks. We have three famous examples or classes of examples for malware: viruses, worms, and Trojan horses. You need to know the differences between these three examples. We have viruses, type of malware that is executable file that is propagated by inserting a copy of itself into and becoming a part of another program. The important feature or characteristics of viruses is the fact that they spread from computer to computer. So, viruses, executable files, they copy themselves into another program, they become part of that program, and they spread from computer to computer. Second example of malware or malcode includes worms. Very similar to viruses, but worms, they do not require a host program. Worms are in fact standalone software programs that take advantage of system features in order to travel through the network. So for worms, remember, they're standalone and they travel through the network. Trojan horses, users are typically tricked into loading and executing Trojan horses, this malware, on their systems. With that, they usually create backdoors to give malicious users access to the system. So it's you at the end of the day that are tricked into loading and executing this specific malware, and then this malware is going to create backdoor for the attacker. Then we have a second class of network attacks. Here we have reconnaissance attacks, discovery and mapping of systems, discovery and mapping of services and vulnerabilities. In a reconnaissance attack, a hacker could use either NSLOOKUP or WHOIS in order to determine the IP addresses assigned to an entity. NSLOOKUP queries your DNS server in order to get an IP address for the IP name that you have provided. Humans, of course, they like to use names rather than numbers. Computers only use numeric addresses, hence the purpose of DNS. NSLOOKUP can also do a reverse lookup to return back from your DNS server the name if you entered an IP address. WHOIS, on the contrary, looks up the domain registration. And remember, domain registration has nothing to do with IP addresses. Domain names are in fact registered but may not even be implemented, therefore may not be allocated or assigned to an IP address. Not until a domain is actually implemented at a web host provider, you or someone else, to provide a site that uses that domain name, is an IP address even involved. A WHOIS only lookup won't tell you the IP address of a domain, but instead it tells you to whom that domain is registered and from whom that domain is leased. That's the difference between NSLOOKUP and WHOIS, and you should be aware of that. So WHOIS is going to tell you the registrant and the registrar, but not the actual IP address of the domain. So for reconnaissance attack, in order to discover and map the system services and vulnerabilities, we have used, let's say, NSLOOKUP to find out the IP address and then the registration information of the domain name using WHOIS service. Next step, once they have the IP address, we need to use fping in order to ping a range of IP addresses to see who is responding. What is the difference between ping and fping? Like ping, fping also uses ICMP echo requests in order to determine if the target hosts are responding. But the similarity ends here. Contrary to ping, which only accepts a single IP address as a parameter, fping can be called with many target IP addresses. And that's why we use fping, not normal ping. Once they know what IP addresses are responding, they could use nmap to see which ports are listening. So the next step is to use nmap, because we know which IP address is responding thanks to fping. Now we use nmap to see which ports are listening. Nmap can be used in order to scan a range of IP addresses for open ports. And open ports is what we love as attackers. This is a command line utility, but for those who prefer graphical user interfaces, its developers have published ZenMap, similar to Nmap, but a GUI front-end based software for this powerful software. Both packages can be installed on different operating systems, including Windows, Linux, Unix, OS X. They are all capable of running these two packages. Then we have the third class of attacks, access attacks. Access attacks include the unauthorized manipulation of data, unauthorized manipulation of system access or user privileges. What happens at the end of the day with access attacks is that access attacks exploit known vulnerabilities in authentication services, vulnerabilities in FTP services, and known vulnerabilities in web services in order to gain entry to web accounts or confidential databases or access other resources. This is what happens. Four classes of access attacks include password attacks, trust exploitation, port redirection, and very famous one, man-in-the-middle attack. Password attacks, this is where hackers can use several methods, including brute force attacks, or Trojan horse programs, or packet sniffers. They all can be used by hackers. The Trojan horse programs, a very famous example is keystroke logger. This software can be used by attacker to conduct password attacks. Trust exploitation, an attacker can access a target system by taking advantage of a trust relationship between the target system and the one that is compromised. This is very, very interesting attack. Port redirection, a hacker installs software on a compromised host and uses that host in order to gain access to a target host on a different port. So that is known as port redirection. And then we have man in the middle. An attacker inserts himself in the middle of a conversation. A common type of man in the middle attack is a phish email that a victim clicks on a link in their email. Finally, we have DOS, or denial of service. This is about disabling or corruption of networks, disabling or corruption of systems or services. DOS, or denial of service attacks, prevent authorized people from using a service. How? By using up system resources, such as disk space, bandwidth, and buffers. The attack can be caused by resource overload or malformed data. So it's not always overload. We can send malformed data, and that causes the victim to fail, hence corruption of service or disabling the service. DOS attacks are the most publicized attacks in network security and the most difficult to eliminate. Some examples of DOS attacks here: we have ping of death, we have SYN flood attacks, we have DDoS or distributed denial of service, and we have Smurf attack. Smurf means experienced gamer posing as a newbie. Here we want to see Smurf attack as a variant of DOS attack. With ping of death, what happens is an attacker sends a malformed or a very large ping packet to the victim. What happens is that the victim fails to process a malformed packet. With SYN flood, an attacker sends multiple SYN requests to a web server, very famous one. The web server waits to complete the TCP three-way handshake, and this is while a valid user tries to send genuine SYN requests to the web server. But guess what? The web server is unavailable. Next, distributed denial of service. An attacker uses many intermediate hosts, and these intermediate hosts are known as zombies, to launch an attack on the victim host or server. Zombies or intermediate hosts used to launch the attack are usually infected with malware themselves, and this gives control to the attacker. So before the actual DDoS attack, the attacker uses malware, and this is used in order to infect zombies, who then in turn conduct an attack on the victim host or on the victim server. A Smurf attack, an ICMP-based attack where an attacker broadcasts a large number of ICMP packets using the victim's source IP address. And that's why we say the attacker is experienced, not a newbie, because he is using the victim source IP, is generating ICMP-based packets, broadcasts a large number of them using the victim source IP, and that causes the zombie hosts or intermediate nodes to reply to the target victim in an attempt to overwhelm the WAN wide area network link to the destination or to the victim IP address. Now that we have discussed network attacks, let's see what mitigation techniques we have in place for these attacks. We have firewalls. Firewalls are one of the most effective security tools available for protecting users from external threats. Network firewalls reside between two or more networks in order to control the traffic between them and help prevent unauthorized access to network resources. We have host-based firewalls and we have network-based firewalls. Host-based firewalls or personal firewalls are installed on end systems. Firewalls use different techniques in order to determine what is permitted or what is denied. 4 techniques used by firewalls discussed here include packet filtering, application filtering, URL filtering, and SPI, stateful packet inspection. With packet filtering, firewalls prevent or allow access based on addresses, be it IP addresses, be it MAC addresses. Prevents, allows access by specific application types based on port numbers. Second kind of techniques used by firewalls is application filtering. It prevents or allows access by specific application types based on port numbers, because different applications are assigned to different port numbers. Third category of techniques used by firewalls include URL filtering, when it prevents or allows access to websites based on specific URLs or keywords. Finally, we have stateful packet inspection or SPI techniques used by firewalls. They follow a simple rule. Incoming packets must be legitimate responses to requests from external hosts. In other words, traffic coming in through the firewall from the outside world must originate from the inside world. So we only accept traffic that is originated from the inside network unless specifically permitted. Next up, we have network baseline. We want to create a network baseline. We want to establish a network baseline because it is one of the most effective tools for monitoring and troubleshooting network performance. So establishing a network baseline in order to monitor and troubleshoot performance. Creating an effective baseline is accomplished by measuring performance at different times, at various times over a period of time. Not just one snapshot, that is not enough at all. One method that can be used is to copy and paste the results from a ping command or from a trace command or other relevant commands into a text file with a timestamp. Don't forget that. Corporate networks, however, they can use extensive baseline statistics using professional-grade software tools. We have ping. The use of ping command is a very effective method in order to test the network connectivity to a particular host or to a particular server or to a particular device. It is an important first step in troubleshoot and troubleshooting for a network failure once detected. The ping command uses, as I said before, Internet Control Message Protocol ICMP in order to verify layer 3 connectivity. We have another variant of ping known as extended ping, and this mode is entered by typing ping, just ping without a destination IP address in privileged exec mode on Cisco machines. Just type ping and press enter, and that means we can have a wide range of options to take advantage from. We can force or change the source IP address for the ping, unlike the standard ping. This is very useful when you do troubleshooting. A ping issued from the iOS, in our case here Cisco router, let's say, will yield several indicators. The most common ones are exclamation mark, dot or period mark, and U, that stands for unreachable. These three indicators. With exclamation mark, it indicates receipt of an ICMP echo message, and this is exactly what you're going to see if your ping results are successful. In other words, you can successfully reach the destination IP address in layer 3. Period or dot indicator indicates a time expired while waiting for an ICMP echo reply message to be received. U, another indicator, the third one, stands for unreachable because an ICMP unreachable message was received. On the other hand, we have trace. A trace returns a list of hops as a packet is routed through a network. What is hop? Each router is a hop. When using Windows machine, then trace becomes tracert command. And when performing a trace from a router, Cisco router CLI, then you use trace route command. Different names, but the same concept. We can have a request timed out response from tracer, trace route, or trace, indicating that the router did not respond. It is possible due to two different causes. There is a network failure, this is the first cause, or the routers were configured to not respond to echo requests used in the trace. So it's not always the case that you can say when request timed out responses are received after issuing trace, that means we have a network failure. No, sometimes routers were configured to not respond to echo requests. Last but not least, while ping sends ICMP packets, traceroute or tracert or trace, they send IP packets with TTL value 30 by default. So ping uses ICMP, but trace uses IP. And that's why we have our TTL values.